Let's summarize what we know an inductor is. An inductor is a conducting coil used to store potential energy in the magnetic field it generates. An inductor will resist changes to the current running through it, generating an EMF to oppose changes in its magnetic flux. The inductance of a device depends on only the geometry of the inductor. I just used the word inductance. Inductance is the measure of the ability of an inductor to store magnetic potential energy, and it's defined as the ratio of magnetic flux through the inductor to the current it carries. The unit of inductance is called the Henry, and 1 Henry is equal to 1 Tesla meter squared per amp. Though inductance of an inductor is defined as the ratio of the magnetic flux through it to its current, it just so happens that the inductance of a device depends only on the geometry of the inductor. This is despite the fact that magnetic flux is equal to the product of magnetic field and area. Let's take a moment to show that the inductance of a solenoid of length L, cross-sectional area A, and number of coils N is given by the relationship of the ratio of the product of the permeability of free space, the square of the number of loops, the cross-sectional area of the solenoid, to the length of the solenoid. We're going to show that the inductance of a solenoid is equal to the product of the permeability of free space, the number of loops squared of the solenoid, the area of one of the solenoid's loops over the length of the solenoid. To help us with our proof, let's sketch a solenoid. So this solenoid has length L. The area of each loop is A, and I'll indicate the area vector pointing to the right. This inductor has N number of loops, and it has a current circulating from right to left. To help us with the orientation of this current, let's indicate using a series of X's or dots, where X's indicate that the current is going away from us, and a dot indicates that the current is coming towards us. So we see that as this current flows through this solenoid, at the bottom of the solenoid, the current's going away. At the top of the solenoid, the current is coming towards us. Now, this is useful because since we know that this inductor has a current running through it, we know that it generates a magnetic field. And that magnetic field is along the central axis and it's uniform. And to determine the direction of the magnetic field, we could use the version of the right-hand rule that says curl your fingers in the direction of current. And so we're going to take the fingers of our right hand. We are going to curl them in the direction of the current. So as you can see here, as we take the fingers of our right hand and curl it in the direction of current, our fingers are coming towards us at the top, and they would go away from us at the bottom. And the direction of the thumb is the direction of the magnetic field along the central axis of the solenoid. So let's indicate that the magnetic field is going to the right. And since the magnetic field is going to the right along the central axis of the solenoid, this solenoid has a magnetic flux. Now remember, we defined inductance to be equal to the ratio of magnetic flux to the current through the inductor. So let's determine the magnetic flux of this solenoid. Remember, magnetic flux is equal to the integral over the area of the dot product of the magnetic field with the area. Let's rewrite the dot product using the version that says it is equal to the product of the magnitudes of each vector times the cosine of the angle between the two vectors. And in this case, the two vectors we're concerned with are the magnetic field and the area vector. So notice from our diagram that the area vector and the magnetic field are parallel. So the angle between them is equal to 0 degrees. The cosine of 0 degrees is equal to 1. This means that we can rewrite magnetic flux to be equal to the integral over the area of the product of the magnitude of the magnetic field and the area differential of a loop. Previously, we've shown that the magnetic field along the central axis of a solenoid is equal to the product of the permeability of free space, the number of loops of the solenoid, the current running through the solenoid over the length of the solenoid. So we could plug this into our integral, that the flux of the magnetic field, or the flux due to the magnetic field in the solenoid, is equal to mu naught n I over L times the area differential. Now notice this magnetic field is constant because the permeability of free space is constant, the number of loops is constant, the current is constant, and the length of the solenoid is constant. So we could pull those constants outside of the integral, and we end up with those constants, mu naught Ni over L, times the integral over the area of a loop. And that integral is very easy to evaluate. The integral of a differential is just the quantity represented by that differential, in this case, the area. So we could write that the magnetic flux is equal to mu naught n, the number of loops, I, the current, A, the area of a loop, over L. What we have found here is the magnetic flux of one loop of the solenoid. We need the total magnetic flux of the entire solenoid, and the entire solenoid has n loops. To get the total magnetic flux of the solenoid, all we need to do is to take the result for the magnetic flux of a single loop of our solenoid and multiply it by the number of loops. When we do that, we end up with the total magnetic flux of our solenoid to be equal to the permeability of free space times the number of loops squared times the current times the area of a loop divided by the length of the solenoid. So now, to determine the inductance of our solenoid, we just have to take the magnetic flux of our solenoid and divide by the current running through the solenoid. And when we do that, that is just simply mu naught n squared IA over IL. And notice a current in the numerator cancels with a current in the denominator. What we have left now is the result that we are looking for, that the inductance of a solenoid is equal to the product of the permeability of free space, the number of loops in the solenoid squared, the area of a loop in our solenoid, divided by the length of our solenoid. This result reminds me of what we determined for capacitors. Because remember, the capacitance of a capacitor depends only on the geometry of the capacitor. And now we have another circuit component, an inductor. Notice that this result depends on only the geometry of the inductor, not on the current, not on the magnetic field. It depends on the length of the inductor, the area of a loop of our inductor, and the number of loops in our inductor, which is a solenoid.